For most of human history, Venus has appeared to us as nothing more than a bright, steady light near the horizon. But behind that calm glow lies a world that refuses to fit into the rules of planetary science. Venus is almost the same size as Earth, made of similar materials, and formed in the same early solar system environment. By all logic, it should have been a second habitable world. Instead, it evolved into the most extreme environment known on any rocky planet. Here, the surface temperature rises high enough to soften or melt common metals. The pressure matches conditions at the bottom of Earth's oceans, and sunlight barely survives a journey through the thick layers of toxic clouds. Something in Venus's past pushed it off the path Earth followed, and scientists are still trying to understand what that something was. When early radio measurements began hinting at intense surface temperatures, many researchers assumed an error. But the more data we collected, the clearer it became that Venus was not simply warm. It was in thermal chaos. An enormous greenhouse effect locked heat in, and the planet spiraled into a runaway climate transformation that has never stabilized. The mystery deepened when spacecraft images provided the first global views. Beneath the bright clouds, the surface is remarkably young, showing evidence of near-planet-wide resurfacing events, catastrophic episodes when molten rock may have flooded across vast regions. No other world in the solar system shows anything similar. Even stranger, Venus rotates backwards compared to every major planet. Its day is longer than its year, and its atmosphere races around the planet in a way that defies standard circulation models. All these anomalies point to a deeper story. Venus is not simply hostile, it is fundamentally different, shaped by processes we still struggle to explain. To decode what truly happened here, we must examine Venus layer by layer, beginning with the strange behavior of its massive atmosphere. The atmosphere of Venus is the key to understanding nearly everything unusual about the planet. From orbit, the upper layers appear smooth and uniform, but when viewed in ultraviolet, complex bands and dark streaks emerge, patterns created by chemical compounds that absorb light in ways scientists still cannot fully identify. These upper layers move at tremendous speeds, completing a full rotation of the planet in just 4 days. This phenomenon, known as superrotation, is so extreme that no existing atmospheric model predicts it naturally. Deeper down, the clouds grow denser and more hostile. Droplets of sulfuric acid dominate the middle layers, forming an enormous reflective shield that traps the majority of incoming sunlight. Only a fraction of the sun's energy reaches the lower atmosphere, yet the heat remains. Thick carbon dioxide beneath the clouds prevents thermal radiation from escaping, generating a greenhouse effect over 100 times stronger than anything on Earth. Near 50 kilometers altitude, an unexpected region appears, a layer with pressures and temperatures surprisingly similar to Earth's surface. Some researchers have suggested that microbial life could potentially survive here, protected from the inferno below. But any optimism fades quickly as we descend further. The atmosphere grows so dense that it behaves almost like a fluid. Winds drop to an almost motionless crawl. Heat distortions become constant, and radar mapping from past missions shows a landscape underneath that has been repeatedly reshaped by volcanic activity. NASA's Magellan spacecraft revealed that around 85% of Venus's surface consists of volcanic plains. Massive shield volcanoes dominate the terrain, while long lava flows stretch for hundreds of kilometers. Some features, called coronae, suggest rising plumes of hot material forcing the crust upward before collapsing again. Evidence re-examined decades later revealed that volcanic activity likely continued during the 1990s, long after scientists assumed the planet was geologically inactive. Venus, it appears, is not a silent world. Its surface and atmosphere interact through cycles of heat, pressure, and chemistry that are still unfolding today. Reaching the surface of Venus means entering one of the harshest environments known. The pressure is equivalent to standing under a column of water nearly a kilometer deep. The temperature stays nearly constant from equator to pole, day to night, because the thick atmosphere traps heat so efficiently that the entire surface behaves like a giant kiln. When the Soviet Venera landers touched down, they lasted minutes before collapsing under the hostile conditions. Yet in those brief windows, they captured images that remain unique in the history of space exploration. The landscape appears barren, fractured, and dry. Rocks show no evidence of erosion by water. Instead, they look cooked under relentless heat. The ground is covered in basaltic flows that hardened into broad plains, interrupted by ridges and scattered boulders. Radar imaging complements these rare photos. High-resolution scans reveal that the surface lacks the abundance of impact craters found on the Moon or Mars. This scarcity suggests that the planet's crust was renewed relatively recently, perhaps through global-scale volcanic resurfacing. Equally intriguing are the tessera regions, highly deformed highlands with patterns unlike any other terrain in the solar system. These ancient fragments may represent the last preserved pieces of Venus's early history, surviving cycles of destruction that erased other features. Infrared studies also reveal unusual hotspots, hinting at active lava beneath the crust. Atmospheric measurements show variations in sulfur dioxide levels that rise and fall in ways consistent with volcanic activity, and the discovery of potential atmospheric anomalies, including chemicals that form under unusual conditions, suggests that Venus's environmental systems are far more dynamic than once believed. If these changes are ongoing, then Venus is not simply a relic of a catastrophic past. It is a planet in evolution, driven by internal heat and atmospheric instability. Understanding these processes brings us closer to uncovering why Venus diverged so sharply from Earth. Even with decades of research, Venus continues to resist simple explanations. One of the greatest mysteries concerns its earliest era. Models indicate the planet may once have supported moderate temperatures and possibly oceans. If true, Venus might have begun as a near copy of early Earth. So, what changed? One theory suggests that increasing solar radiation slowly evaporated Venus's water, leaving carbon dioxide behind and accelerating global heating. Another proposes that Venus experienced massive volcanic outpourings that released enormous amounts of greenhouse gases. Without plate tectonics to recycle carbon into the mantle, the atmosphere accumulated heat indefinitely, yet these answers remain incomplete. Venus's slow retrograde rotation is itself an anomaly. It may be the result of a colossal early impact, or it could be a long-term consequence of tidal interactions between the dense atmosphere and the planet's surface. Determining which explanation is correct requires more data than we currently possess. That is why a new generation of missions is preparing to return to Venus. NASA's Da Vinci mission will plunge a probe through the atmosphere, taking high-resolution images and analyzing chemical signatures all the way down. Veritas will map the surface with radar far more advanced than the tools Magellan carried decades ago. ESA's Envision spacecraft will study the planet's interior structure, geology, and atmospheric processes. Together, these missions may reveal whether Venus still hosts active volcanoes, whether its crust undergoes constant deformation, and whether its atmosphere contains compounds that hint at a long-lost habitable era. Understanding Venus matters not just to planetary science, but to our future. Venus demonstrates how quickly a world can transform when climate systems destabilize. It also shows us how fragile habitability truly is. If we can decode the planet that should not exist, we may gain insight into how Earth avoided the same fate, and what must be done to ensure it remains stable in the ages to come.